CAS Unit 1 Topic 6 is on the shape of molecules. In the first section, we're going to look at the valence-shell electron pair repulsion theory. When a molecule forms, the outer shell electrons, both bonding and non-bonding, repel one another. The shape the molecule takes is that which minimizes the repulsion between the different pairs of electrons. Lone pair repulsions are greater than lone pair bonding pair repulsions, which are greater than bonding pair repulsions. And multiple covalent bonds are treated as single bonds in terms of repulsion. When we apply the valence shell electron pair repulsion theory to a molecule, it is important that we draw a dot cross diagram of the molecule using only outer shell electrons. We then determine the number of bonding pairs of electrons around the central atom and the number of lone pairs of electrons around the central atom. At that point, once we know the bonded pairs and the lone pairs, we will be able to suggest the shape of the molecule and assign the bond angle. The example below is methane, and it has 4 bonded pairs of electrons and no lone pairs of electrons. We're going to start by looking at molecules that only have bonded pairs of electrons, and there are some examples that are named in your specification. The first example is a molecule where there are only bonded pairs of electrons, and the example is beryllium chloride. The central atom beryllium has 2 bonded pairs of electrons, and these will all repel each other equally to form the linear shape. The bond angle in this case is 180 degrees. If we look at carbon dioxide, it has 2 double bonds. If we treat those double bonds as single bonds, again we will have 2 bonded pairs of electrons that will repel each other equally with 180 degrees, so the shape of carbon dioxide is linear. The next example is where we have 3 bonded pairs of electrons, and our example is boron trifluoride. Boron is in group 3 and has 3 outer shell electrons. And we have 3 bonded pairs of electrons, so again we have equal repulsions that will give us the shape and angle of this molecule. The bond angle is 120 and the shape is trigonal planar. We're now going to look at methane. The central atom carbon has 4 bonded pairs of electrons, so they repel each other equally to form not a cross shape, which would be the greatest repulsion in 2 dimensions, but tetrahedrally, which would be the greatest repulsion in 3D. This gives us a bond angle of 109.5. Another example would be the ammonium ion. The central atom nitrogen also has 4 bonded pairs, so its shape is tetrahedral with a bond angle of 109.5. We are now going to look at phosphorus pentachloride. There are 5 bonded pairs of electrons around the central phosphorus atom. These bonded pairs of electrons repel each other equally, and the molecule takes up a trigonal bipyramidal shape. There are 2 bond angles in a trigonal bipyramid, one at 90 degrees and the other at 120 degrees. You may notice as well that in this molecule, phosphorus does not obey the octet rule as it has 10 electrons in its outer shell. The last example of molecule with bonded pairs of electrons is sulfur hexafluoride. In this case, there are 6 bonding pairs of electrons around the central sulfur atom. These repel each other equally and the molecule takes up an octahedral shape to minimize the repulsions. The bond angle in this case is 90 degrees each time. The term octahedral comes from the fact that the solid shape formed from connecting all the fluorine atoms forms an 8-sided figure called an octahedron. This is a summary slide and it just recaps the different shapes of molecules we obtain with different numbers of bonded pairs of electrons. We are now going to look at some examples of molecules where we have both bonded pairs of electrons and lone pairs of electrons. Some of these molecules will be very familiar, such as ammonia and water. Let's look at ammonia. There are 3 bonded pairs of electrons and 1 lone pair of electrons around the central nitrogen atom in ammonia. The basic arrangement of the electron pairs is tetrahedral around the nitrogen, but since there is no atom attached to the lone pair, all you see is the bottom of the tetrahedron, which looks like a pyramid. The extra repulsion from the lone pair squeezes the bonded pairs of electrons closer together, because remember, bonded pair lone pair interactions are greater than bonded pair interactions, and the extra repulsion from the lone pair means that the bond angle decreases from 109.5 to 107 degrees. This slide compares the ammonia molecule with the ammonium ion. In the case of ammonia, we have 3 bonded pairs and 1 lone pair, so the shape of the molecule is pyramidal. And in the ammonium, we have 4 bonded pairs of electrons, so the shape is tetrahedral. The angle decreases from 109.5 to 107 because in ammonia we have a lone pair of electrons and the lone pair bonded pair repulsion is greater than the bonded pair repulsion. Let's look at exam technique. This question asks about phosphine, which is an analogue of ammonia. Phosphine has the formula pH3. We know it has a pyramidal shape and a bond angle of 107. But we are asked to explain why the angle is 107. Let's look at the mark scheme answer. The mark scheme answer gives 1 mark for the bond angle, but the second mark we have to explain that the lone pair bonded pair repulsion is greater than the bonded pair repulsion, which of course means the angle decreases from 109.5 to 107. If you just recap on the spec, you can see that you're expected to explain the departure of the bond angles in terms of the increasing repulsion between bonded pair, lone pair bonded pair, and lone pair electrons. The next example we will study is water. If we have a look at water, we can see we have 2 bonded pairs of electrons around the oxygen and 2 lone pairs. If we look at the bond angle now, we see the bond angle has decreased further to 104.5 and the shape is bent. Because we now have 2 lone pairs of electrons, the extra repulsion from the lone pairs squeezes the bonds closer, giving the decreased bond angle of 104.5. This is an example of a question that appeared in a past paper to state and explain the shape of the water molecule. In this answer, we need to talk first of all about the shape. We then need to discuss our bonded pairs and lone pairs and the shape adopted to minimise repulsion. So if we look at the mark scheme answer, the shape is bent. There are 2 lone pairs and 2 bonded pairs, and the shape is adopted to minimise the repulsion. It would be appropriate to also state that the lone pair interaction is greater than the lone pair bonded pair interaction. Here are some other more unusual shapes of molecules. This example is chlorine trifluoride. The central atom has 3 bonded pairs of electrons and 2 lone pairs of electrons. The shape of this molecule is T-shaped and the bond angle is 86 degrees. Another example here is quite similar to water in that the shape is bent, but is where we have 2 bonded pairs and 1 lone pair. The 2 examples that are given are sulfur dioxide and the nitrite ion. The final shape we will look at is square planar. This is when the central atom has 4 bonded pairs of electrons and 2 lone pairs of electrons. The lone pairs are arranged at 180 degrees to each other to minimise the lone pair repulsions, and the 4 bonded pairs repel equally. The shape is square planar and the bond angles are 90 degrees. This is a shape that we will meet in more detail in the A2 course. This is a very good summary table of the shapes we have met in this topic. If we look, the most common shapes we need to be aware of are when we have 2, 3 and 4 bonded pairs of electrons. So that is our linear, our trigonal planar and our tetrahedral shapes. And then when we have 3 bonded pairs of electrons and 1 lone pair and 2 bonded pairs and 2 lone pairs, which are our pyramidal and our bent shapes. If you have a look, you will see examples of molecules that you are familiar with. A good examiner tip is to learn one molecule for each shape in detail, and then it will be easy to compare any unknown ones which may arise in an exam question.